Okay, so hello everyone, my name is Carlos Raque, I'm from Porto. I'm developing my master thesis at IFIMUP and I'm going to share with you the work I'm developing for this thesis, which is to study topological insulator materials and plasma modes on these materials and try to establish sort of a connection. And we are focusing on the case of bismuth and tellurium, which is a well-known topological insulator material. Well, as a motivation, as we all know, as society, we depend on technology, and technology depends on non-magnetic semiconductors, and these are now facing a fundamental limit in terms of their performance due to several problems. One of them is the restrictions of miniaturizing these materials, and because of that, a new paradigm is needed to overcome this issue. And because of that, the spintronics area emerged, suggesting that we should use the spin degree of freedom instead of the charge of the electron to process, transfer, and encode information. And one of the main focus of this area is to find materials that exhibit spin-dependent phenomena. One of them are topological insulators. They are widely known for their electronic properties that are really interesting and also exotic. They are defined by having an isolating bulk and at the same time, topologically protected metallic surface states. These states are described by the three-dimensional direct Hamiltonian, and from this Hamiltonian is theoretically predicted that at high symmetry points of the Brillouin zone, the band gap should close in a structure called direct cone, and this also was experimentally observed by ARPS measurements. Here you have an example with bismuthium selenium, which is a well-known topological insulator material. Well, the topological features of these materials are widely studied now in the spintronics area, but with this work, we propose something rather different. Instead of studying these properties, we want to study plasma modes on these materials that are normally linked with the terahertz region of frequency excitation. And because it's theoretically predicted that when exciting a plasma mode on these materials, a transverse spin wave is excited alongside. So we want to study the influence of this theoretically predicted spin wave on the already studied topological features of these type of materials. For that, we have to tailor the samples because one of the ways to excite plasma modes is to tailor the samples with grating structures. For that, we use this method, which is called nano-imprint lithography, in which we have a stamp with inverse nano micro grating structures we want to transfer to the substrate. We apply high temperature and high pressure to this stamp and to a thermoplastic polymer. And because of that temperature and pressure, we can induce a phase transition in this polymer and for that to become more viscous and adapt itself to the cavities of the stamp and therefore can acquire this pattern. We done that. Firstly, we fabricated the stamp. We use CDs and DVDs for that because they already hold the grating structures we want to pass, as you can see there in the picture, and we use speed MS to produce this stamp. Then we passed on to the substrate we choose, that was PMMA. We choose to pass both with CDs and DVDs because they differ on periodicity, and by changing the periodicity, we can change the frequency of excitation of the plasmon. So we have different plasmon modes, and that's of interest for us. And then we measure by X-ray diffraction our samples, not the grating ones because we cannot measure under X-ray diffraction, but the thin film. We use PMMA as a substrate that I already told you. Then we use bismuthium tellurium as the topological insulator material. And then we deposited a silver layer on top of that because it's easier to excite plasma modes on silver. And then we can couple the plasma from the silver to the bismuthium tellurium and take advantage of the properties of the topological insulator material. As you can see in the X-ray diffraction spectrum, we don't have any peaks. We identify an amorphous structure. And we think that's because of the fact that a PMMA is also an amorphous substrate. Then we did some numerical simulations because Plasmonics is really dependent on geometry parameters. We want to sweep some geometrical parameter, mainly the thickness of the materials, in order to observe the difference in the optical spectra and in the plasmonics response. We swept the silver thickness and then the bismuthium tellurium thickness. In the silver is where the plasmon is being excited, so most of the plasmonics events should be focused there. But in both of the sweeps, we identify three main peaks that we believe that come from the plasmonics events. And as you can see, there is frequency shifting when increasing both of the thicknesses. So we study this frequency shifting for both of the layers. And as you can see, they are rather different, and this is expected because optically these materials are rather different, so different behaviors are also already expected. And then focusing on the silver one, you can see that the wavelength of excitation increases for increasing thickness of the silver up to a thickness of 30 nanometers. Above this thickness, we overcome the skin depth of the silver for this wavelength, so the wavelength stays fixed. And this feature is also observed for the second peak. And concerning bismuth tellurium, we have different behaviors. And then concerning the third peak, we have the opposite behavior for the silver thickness sweep. The wavelength of excitation decreases with increasing thickness of the silver layer. This matches with the literature reported data for the silver thickness for silver gratings. So we believe that this is a plasmon that is excited or in the interface between silver and air or silver and the substrate, whereas the other previous two are excited with the silver interface with the bismuth tellurium. As there is no reported literature data from gratings with these two materials, we believe that that's the case. Then we measured our samples for the different type of structure with only with a substrate, then a film with both materials, a grating with both materials, and two gratings with one of them to try to identify different contributions in the optical spectrum. Firstly, the PMMA substrate doesn't have any optical signal as we were expecting because it's highly transparent. Then the film exhibits increasing absorbance with decreasing wavelength, and this is present in the gratings. So this comes from the interesting optical properties of the materials and not from Plasmonics events. Then we observe that when changing from films to gratings, the absorbance is increased. And then you can see that we can match some of the peaks of the gratings with only one of the layers and the gratings with the two layers. So the first two peaks of the gratings with bismuth tellurium and silver are from a bismuth tellurium contribution because those peaks match. And the last peak comes from a silver contribution since it matches with the only silver grating. Then we measure the sweep of bismuth tellurium as we did in the simulations. And as you can see, these sweepings are rather different comparing with the simulations. We are aware that there are some differences between simulations and experimental data, the experimental conditions, but we found that it was rather strange. So we tried to image the structures after the measurements, and we observed that these were completely or slightly damaged. And this makes sense because if we are damaging or even destroying the geometry asymmetry of the system, we have to expect that the optical and plasmonics response is not the same. Then we try to measure the transport properties with no light shine on. So we are not exciting plasmonics modes in this yet. We measure for a film and a grating with bismuth tellurium and silver. The results are similar, so tailoring the sample does not affect the transport property, namely the resistivity dependence on temperature. Then we apply the most variable range hopping model because it's the more adequate model for resistivity measurements in high disorder systems. And we observe that our data exhibits a dimensionality of 0, which is often linked with quantum dots. So what we believe is that as we already identified an amorphous structure in the X-ray data, our system has an intergrain resistance so big that it behaves as an ensemble of quantum dots. Then we measure the magnetoconductance. We already did this in the research group IM with bismuth tellurium and Captain. We observed the emergence of the weak antilocalization effect, but with these new results, we observe a competition between the weak localization and the weak antilocalization effects. We find this a bit odd, so we try to identify from where this came from. The silver layer, we measure again this sample and then a sample with only bismuth tellurium and then a sample with bismuth tellurium silver but tailored with grating structures. And we verify that all data exhibit this competition between these two behaviors. So this competition does not come from the silver layer on top. We think that it comes from the amorphousness of the substrate that is so amorphous that localize the electrons, and then the weak localization effect emerges because of that. Well, as future studies, there are several things to be done. We also want to continue these measurements, study the effect of periodicity, because all these measurements occur with a DVD typical periodicity of 700 nanometers. Then we want to include a magnetic layer and study the magnetoconductance while exciting plasma modes, and the same thing with ferromagnetic resonance measurements. This is all. Thank you for your attention, and I'm available to answer to your questions.
Thank you very much for your talk.
Thank you.
So the floor is open for questions. So I will start with a quick question. I don't know, I didn't understand exactly. You showed the thickness dependence, and then you said that your sample got damaged. Was it for interaction with the light, or do you know what was the cause?
That is still a work in progress. We don't know yet why they are damaged. We believe that's related to sample preparation because we use a certain procedure, and after treatment with alcohol, we think that it can damage the polymer from the DVDs, but that's still in development. I cannot advance with 100% certain that that's because of that.
Okay.
Sylvia, can I ask Sylvia?
Yes.
Thanks a lot for your nice talk. Do you comment in the rebel in your magnetoresistance measurement? You have rebels in the measurement, in the experimental measurement.
Yes, these are experimental results. I don't know if I understood correctly the question.
So I mean the rebel, this noise level.
Yes, there is a bit noise. Yeah. We found out that there is more.
Of such noise. What could be the source of this noise?
Okay, when measuring the grating structures, all of the samples exhibit a lot of noise. So we believe that comes from the fact that these samples are, well, we have the tailoring of the structures. But there are some films that also exhibit this noise. We think that comes from a contact issue, bad contact to the sample, and it naturally exhibits some noise.
I see. Okay.
Thank you for your question.
Any more questions? I think we still have time for one or two. Okay, if not, then I would like to thank again all the speakers of this session.